Max Planck kicked off this whole light emission saga with his flashy idea that energy isn't just spilled everywhere like your roommate's dirty laundry, but instead, it's emitted in neat little packets known as quanta. This groundbreaking thought was like the spark that lit the quantum mechanics bonfire. Who knew that tiny little energy bits would lead to a whole new way of looking at science? Then came the ultraviolet catastrophe, which sounds like a sci-fi movie, but was actually a major hiccup in classical physics. It was a bit like predicting that you'll win the lottery every week, only to find that your bank account is as empty as your fridge on a Sunday night. This baffling contradiction between theory and experiment sent scientists scrambling for answers. Cue the light bulb moment. And wouldn't you know it, the photoelectric effect sauntered in and threw everyone a curveball. It showed that light can strut around acting like both a particle and a wave, which was like discovering your cat can both purr and fetch. Mind-blowing. This revelation didn't just shake things up, it tossed classical physics out of the window and sent quantum theory rocketing into new territory. As scientists toiled with gold leaf electroscopes, which honestly sound like a fancy art project, it turned out only high-frequency light could coax those shy electrons out of metal. Surprise! This was the opposite of what everyone thought light would do, proving that science sometimes has a better sense of humor than we do. The photoelectric effect also had a little secret to share. Light's energy is like a party, it's all about the frequency. The higher the frequency, the more energetic the party gets, unlike those boring low-frequency light parties. It wasn't until clever experiments with different light colors that this relationship became clear, proving that light knows how to keep things interesting. Then came Einstein, strutting in with his revolutionary theory, light as particles called quanta. These quanta were like mini energy bouncers, each carrying energy based on frequency. Suddenly, the photoelectric effect made sense, like piecing together a jigsaw puzzle after a week of confusion over how many corners those pieces had. Meanwhile, Rutherford was busy conducting his famous gold foil experiment, which revealed that atoms aren't just dense little blobs but have a sophisticated structure with a nucleus at the center. It was a big revelation, like finding out your seemingly ordinary neighbor is actually a secret agent. Talk about a shake-up in our understanding of what makes up the universe. Then enters Bohr with a revolutionary atomic model that explained why electrons weren't just bouncing around like kids on a sugar high. Instead, they stuck to quantized energy levels, providing some much-needed stability. This was a pivotal moment for quantum theory, as it tackled those pesky paradoxes surrounding how electrons behaved, giving physicists something to smile about. De Broglie wasn't about to let the excitement die down. He proposed that even particles like electrons could wave their hands, exhibiting wave-like behavior. It was like a cosmic dance party where waves and particles were finally invited to the same bash, bridging the gap between two worlds that had been at odds for too long. In a mind-blowing turn of events, some experiments showed that electrons could create diffraction patterns, akin to how light interacts with a grating. It's like discovering that electrons enjoy a good rave. Even more astonishing was the fact that single electrons could produce interference patterns over time, reinforcing the idea that these tiny beings could interfere with themselves. Talk about being your own worst enemy. Out of this scientific mess emerged Heisenberg's matrix mechanics, steering away from classical deterministic views and focusing instead on what we could actually observe. It was like throwing your horoscope out the window and saying, "Let's deal with the facts, people." This laid down the mathematical framework essential for understanding the quirky world of quantum phenomena. Next up, Schrödinger introduced his wave function, which was initially taken at face value as the real deal, portraying particles as actual waves. But hold your horses. Max Born threw a wrench in the works by interpreting it as a probability amplitude. It was a classic case of what did you just say? In the quantum world. The Copenhagen interpretation came to the rescue, claiming that particles exist in a state of superposition until someone peeks at them. It's like your messy college roommate who only cleans up when company is coming over. This highlights how the observer plays a crucial role in shaping reality, making sure we know who's really in charge. Now, Einstein wasn't just sitting back and letting all this probabilistic nonsense slide. No way. He believed reality should have a life of its own, independent of whether we're watching it or not. His concerns came to a head with the genius Einstein-Podolsky-Rosen paradox, which made many a physicist raise their eyebrow in disbelief. Einstein even used gloves as an analogy to explain his point, suggesting that particles have definite states before we measure them. Picture this: gloves that always know how to be left or right, irrespective of who's looking. This illustrates his classical view, proving he was not ready to give up his traditional physics beliefs just yet. Dirac stepped onto the scene with his groundbreaking equation predicting antimatter, which was revolutionary for quantum mechanics. It was the scientific equivalent of finding out there was an alternate universe where cats walk their owners. Mind-blowing. This discovery led to the positron, which helped bridge the gap between theory and experiment in the dazzling world of physics. Then we have Pauli strutting in with his exclusion principle, explaining why electrons arrange themselves in atoms like they were forming a quirky student group for a project. This laid the foundation for understanding the periodic table and all those weird chemical properties, including why some elements are best buddies and others just can't stand each other. It was all about that electron spin. The Pauli exclusion principle became essential in explaining why electrons, protons, and neutrons can't squeeze into the same quantum state. It's like a crowded dorm room. This principle is critical for understanding how matter behaves in different phases, which is a fancy way of saying it helps explain why your soda fizzes and your ice cream melts. Quantum field theory entered the chat to bridge the gaps between quantum mechanics and special relativity, serving as a framework for understanding particles as excitations of fields. It was like fitting the pieces of a giant puzzle, helping us establish the standard model of particle physics, the ultimate science club for particles. Quantum electrodynamics took the stage by linking electrons and light, revealing their interactions at the quantum level, and showcasing the deep symmetry between light and matter. This connection is like the perfect double date in the physics world, reminding us that light and matter are entwined in a cosmic tango with significant implications for fundamental forces and technology. The success of quantum electrodynamics is evident, providing predictions that match experimental observations remarkably well. It's like having your cake and eating it too. This solidified its place as a leading scientific theory, proving that when the quantum world speaks, we'd better listen. John Bell's theorem waded into the ongoing debate about quantum reality, demonstrating through inequalities that local realism just doesn't hold a candle to quantum mechanics. It led to experimental validations, which left many scientists with their jaws on the floor and their minds blown. Roger Penrose added his thoughts, critiquing quantum mechanics and arguing for a deeper understanding that includes gravity, because who doesn't love complicated relationships? His suggestions hinted at a more comprehensive framework that could unravel the universe's true nature, making us all question just how much we really know. So, folks, strap in because the quantum journey is wild. Who knew that diving into the world of particles could lead to so many twists and turns? Remember, in quantum physics, just like in college, expect the unexpected, and keep that curious spirit alive.